Great. So we have Benjamin Basso, and he will tell us about the Regge limit of polygonal Wilson loops.
Thank you very much. I'd like to start by thanking the organizer for organizing this very nice conference here in Stockholm. It's always a pleasure to be back in Stockholm. It's my first time at KTH, but I am Stockholm in general. I will also I'd like to start by begging also the organizer pardon for not doing what they were expecting me to do, which is to give you some review talk, I guess, about the collinear limit of scattering amplitude, the Flux-tube, this kind of constructions, the Pentagon transition, and so on. I don't know what happened, I screwed up, I kind of forgot. And what I decided to do is the exact opposite. I will be talking about something which is unpublished and still work in progress. So there will be many question marks and probably equations which are not that right. But maybe it can be more exciting than, I don't know, reading some other stuff. Anyway, so here is a kind of tentative title. I don't know what the paper, if the paper P1 will be about exactly, so that's a bit vague. It's about the Regge limit of polygonal Wilson loop. So the two main corners that I will be discussing are two important kinematical regimes for scattering amplitude and light-like Wilson loop. So here is, you can consider this as a sort of review slide. In plan equal to 4 superior means, which is the only theory that I will be discussing and considering here. Gluon scattering amplitude, color order of Gluon scattering amplitude are exactly equal to light-like polygonal Wilson loop with a contour which is drawn, which is made out of the momenta of the gluons that we are injecting. This looks like a very innocent equation. It's not immediately clear how much we can get out of it, but for people who know a little bit the story, they know that this is really like, that was really like the beginning of a lot of development and a lot of progress in this field. So in particular, on the Wilson loop side, because we are dealing with a green function of sort, a non-local green function, but still a green function, and because the theory is a CFT, we can use some very powerful techniques, CFT techniques, for analyzing what is happening when two edges here are becoming collinear. So this is a limit that obviously simplifies the object, starting from a big object that can have, I don't know, thousands of edges. We can apply sequentially some collinear limit and start flattening some cusp at the bottom or on the edge or at the top. And this way reduce the complexity of the object. So this is the idea which is behind the OPE, that I will briefly review on the next slide, and which gives us a lot of information and control on this non-polygonal Wilson loop at finite coupling in this theory. The other corner, which is very interesting and very exciting, especially recently, there have been many development and progress in this direction, is the so-called Regge limit. So here the picture is much more transparent and clearer on the scattering amplitude side, where it amounts to taking a particular limit where the particles are all highly boosted relatively to each other. So this is a limit where things also simplify, and this is a limit which is also of phenomenological interest for some real scattering experiment like at LHC and so on. So I will be talking about this two limit, and more importantly I will be talking about their interplay and how to relate them. Try to understand better how these two pictures of the Wilson loop and the scattering amplitude, which are guaranteed to be equivalent of this theory, are actually dialoguing between them. So let me start with my favorite picture. This is a picture that concerns the first point here, the collinear limit. So the idea to make the physics as transparent as possible in this limit is to pick a particular channel. So this amounts just to picking two of the line of the Wilson loop, and to, using conformal symmetry, stretch everything else except for these two lines. So we do some conformal transformation, whose effect is precisely to flatten whatever it has at the bottom and top of these two lines. So we can always do that. We can always find generator that precisely do dilatation in that direction, if you want. So what is happening then is that we are approaching an extremely simple Wilson loop, which is just a square Wilson loop, which we interpret as a ground state, as a reference state for what we call the Flux-tube. The Flux-tube is just the picture that we will get if we cut the Wilson loop at a given time here. So what we will find is some quark here, some massless quark, and an anti-quark at another point. These are just the usual pictures associated with this kind of holonomy with the Wilson line, that they are just classical objects. There are no dynamical quarks in this theory, but we can introduce classical quark in the form of this half-ordered exponential of the gauge field. So these are just a pair of quark and anti-quark, which are not moving, they are not dynamical, they are just there. They are moving, but they are not dynamical, they are not fluctuating. Okay? So they are just moving according, they are just following like trajectories. So at a given time, what we are seeing is just this quark and this quark-antiquark pair that is sourcing a field around them, which is just the chromoelectric flux of the theory. Okay. So the idea is that this flux is created somewhere at the bottom, will evolve over a certain time, and also move from left to right over a certain distance, and eventually get absorbed at the top. So this is this 1+1 picture that we are getting, 1+1 dimensional, because the flux is obviously one-dimensional. It's something that stretches from one point to another. The picture might not be that obvious in the gauge theory, in the original field theory, but it becomes extremely transparent if we go to the string dual, where the Flux-tube, the holographic picture of the Flux-tube is just a string which is ending on the contour of the Wilson loop, and so at a given time it's just stretching from one point at the boundary to another point. Okay. So this is our background, this is our Flux-tube, which is sourced by these two lines, and coming with this picture is a representation for any polygonal Wilson loop or equivalently scattering amplitude as an infinite sum over all the excitations that this Flux-tube can support, with some coefficient here for the propagation of this excitation over some time tau, some distance sigma. There is also some angle phi, because the physics is really taking place in 4 dimensions, so there are 2 extra dimensions that I cannot draw here on this slide, which I can rotate, and there is a chemical potential phi for this rotation that couple respectively to the angular momentum of the excitation with respect to this U1 symmetry, to the momentum of the excitation with respect to shift from left to right, and to the energy of the excitation for propagation in time tau. So this tau, sigma, and phi are just a convenient way in this particular framework of parameterizing the conformally invariant Wilson. So this tau, sigma, and phi, if you want, are directly related to the cross ratio that we can make out of the point of this Wilson loop, and which unambiguously characterizes geometry. So this is for the information for the propagation and the geometry. The leftover information that we need to actually reconstruct the full amplitude are this C coefficient, some sort of OPE coefficient, that encode the probability amplitude for creating a certain excitation psi on this Flux-tube, starting from a particular bottom part with a particular bottom geometry, and a similar quantity C at the top for the annihilation of this excitation. So this is quite surprising that scattering amplitude in the end can be represented by an expression of this type that looks like a partition function or correlator of sorts, and that this representation holds at any value of the Fairfield in particular. Nothing here relies on whether the theory has a marginal Fairfield or not. The only information that we are using is that the Flux-tube exists, and that it can support excitation, and that the theory is conformally invariant. So the Regge limit looks rather different at first sight. So the clearest picture is probably found by starting directly with an amplitude, something that you might be more familiar with. So first of all, it's a limit that controls the high energy behavior of scattering amplitude. So typically when we do 2-to-2 scattering, it's a limit where we fix t, the momentum transfer, the Mandelstam invariant, and we send s to infinity. So in this limits, scattering amplitude are expected to scale at a power law up to some power omega here, some spectrum of powers omega that plays a role of spin in this game, which we need to figure out. Okay? So if we start in the Euclidean regime for the scattering amplitude, we don't find anything very exciting. Or we find something, but it's not very exciting. But the physics got a lot more interesting if we instead go to some Mandelstam region, some Minkowski region, where some of the particles which are in the out state are flipped back to the past. Then when we cut in the middle here, we think about the evolution in this limit as evolving from left to right here, following the rapidity gap between the particles. What we find are more exciting, more interesting quantities which are governed by the BFKL kernel and which are known as BFKL eigenvalues. So these are non-trivial functions of the quantum numbers that we need to parameterize the physics along the plane where we are cutting here. So this is a physics which is transverse to the incoming excitation. And one of the main problems in this business is to understand what are these omegas that we can find, what is the spectrum of these BFKL eigenvalues, and what are the expression at possibly any value of the country. So in the end, when the dust settles and we write down, or people write down precise expression for the behavior of the scattering amplitude, or equivalently the Wilson loop, in these two kinematical domains, what we find are integral of this type, so sum over term. So here, for the OPE, for instance, there is a leading contribution which is just given by the vacuum, the state where the Flux-tube is in the ground state, and then a sum over the leading twist excitation. The leading twist excitation are single particle like, if you want, they just carry a momentum m and some angular momentum. They just carry a momentum p and some angular momentum m, and so are integrated over this momentum, which is the only freedom in the game, with some measure and this phase which I explained before. So these are the leading twists. They dominate at large tau, or if you prefer, these are states which have the lowest possible mass with respect to relevant symmetries and illustration of the tau direction. The terms here are typically subleading. They can involve more particles. Of course, if we can produce one particle, we typically expect that we can produce more. It can also be other single particle states which are given quantum numbers. So here, a given angular momentum just happens to have a twist which is bigger than the one appearing here. For the BFKL expression, so it's an expansion for the same object, but on a different sheet. We need to analytically continue our object through some cut in a very specific way, which I don't have time to explain. But if we do that properly, then we find that the result can again be written as an infinite sum over some angular momentum m here, and an integral over some variable nu that play also the role of the equivalent role of the momentum for the OPE of a similar type of ingredient. So here the leading spin dominate, and the terms which are suppressed are just terms which happens to have negative spin, and so are energy suppressed. So the two formula looks extremely similar. They are in slightly different limit. Here we only need to take tau to be large. Here we need tau plus sigma to be large, which is a quantity which is conjugate to these BFKL eigenvalues. So naively, one could imagine just identifying these two integrals by just redefining, for instance, the identifying energy plus IP with omega and energy minus IP with whatever quantity I give here, which is nu, and maybe get a match. Of course, this is not working. The two pictures are exact. The two expressions are very coupling, but these are two different pictures, two different expansions on two different sheets. So they don't have to match as directly as one could expect. Instead, one finds by, if one compares these two expressions properly, by going to the domain where they overlap, one finds that the leading term in one expansion actually resolves infinitely many terms in the other, and vice versa. So we should expect that the mapping between the two is rather complicated and probably much less trivial than we could have found. But still, the two objects are strikingly similar, and that raises many questions like, why is it so? How can we actually relate the two? So given some information about the collinear limit, can we automatically derive the information in the BFKL regime? And is this analogy just an analogy that holds on for the simplest possible case, which is the hexagonal Wilson loop, or can we actually push this parallelism further and maybe get some insight about either side, the OPE or the BFKL side, or higher polygon and more complicated kinematics. So during this talk, I will try to explain and to present some conjecture for going from the OPE to the BFKL story. So from the knowledge that we can have here, try to derive some information on the other side. So the main reason is, by this time, I don't want to say that we can only go one way. It's actually a good question to ask whether whatever we are going to do is reversible or not. But the reason why I will be starting from the OPE is that the OPE is much more well understood and developed than the BFKL side. Okay? So there is a motivation for starting from here. In particular, in the case of the amplitude, we know very well what we are supposed to sum over. So the state of the Flux-tube that we should all include are in one-to-one correspondence with insertion of the adjoint field of the theory along the light ray. So the picture is rather clear if you remember that we are actually flattening some cusps, say at the bottom of two lines here. And when we do this flattening, the leading effect will just be effectively to replace the two lines by a single line. But if we want to parameterize all the rays, all the subleading terms that will be generated along the way, we naively expect and naturally expect to get insertion of field. And indeed, to leading order, if we carry out the exact computation of expanding this Wilson line, this test Wilson line along a particular direction, we will get many insertion of the field strength tensor, for instance. At higher loops, due to radiative correction, we expect to be able to produce all the possible field of the theory, like the scalar field here, the complex scalar field. We have 3 of them, and the complex conjugate, but also the gauging field and the derivative acting on the field strength tensor. So the only thing that we need to do to understand the spectrum of the theory is just identify what are the linear combinations of field here that are necessary to span all the possibilities, all the options, all the excitation that can propagate on this background. Okay? And in particular, once we have understood that, once we have understood what are the flavor of excitation, we want to get information about their energies, their momentum, all the spectral data, including also their S matrix on the Flux-tube, so the way they interact with each other along this light ray. And this way we will be equipped to develop this Flux-tube picture in all details. So yet another way of thinking about the very same picture, which happens to be in practice much more efficient for extracting data and information at any value of the coupling, is to discretize this light ray direction and replace it just by a very large number of covariant derivatives along this light direction. So intuitively, these are just bits of this link connecting the two fields, for instance, and by putting many of them, we will effectively delocalize the excitation and create an object that looks like what we want. So the good point about it is that once we've done that, this operator becomes a local operator, and so can be embedded in the spin chain integrable setup that people have developed for computing scaling dimension and classifying all these states. So there is a one-to-one correspondence between this Flux-tube state and large spin operator, which allows us to import all this information about the spin chain and its integrable structure, and in particular derive everything that we need to run our program, our OPE program, which are the dispersion relations, the Flux-tube metrics, etc. So all this information has been obtained and is available for whatever use. What is more is that we also know how to build arbitrary polygonal Wilson loop using this Flux-tube picture. So the idea is that if we have a big polygon, what we will do is that we will start drawing some light-like rays, which are not part of the original polygon, we are just drawing them for helping us visualizing what is happening. So we pick a cusp, some cusp at the bottom, and we draw the line, the light ray, which is starting from this cusp and cutting the edge at the opposite. Once we've done that, we go to the other point and we repeat this procedure until we reach the top. So what we get this way is a decomposition or tessellation of our polygonal Wilson loop in sequence of square. So the square is a reference state for our Flux-tube. So this square is just a picture of the dynamics of the Flux-tube at a given time during its evolution throughout the polygonal Wilson loop. So it always starts in the bottom, just because for bosonic Wilson loops there is nothing here that can excite the Flux-tube, and it always ends also in the vacuum of the Flux-tube because there is no excitation at the top. But in the middle square, the excitation can be arbitrary, as we will expect just by the presence of this extra cusp, that essentially kick out the Flux-tube from its ground state and put it in another state, some excited state here, psi1, that can be arbitrary. So what we have to do is to sum over all the possible states in the intermediate channel with the right phase that encodes the geometry of this polygonal Wilson loop, so the center-cross ratio, written in terms of the stars, sigma and phi, which have a nice interpretation for us, and then put some amplitude associated to a particular Flux-tube sequence, starting from the vacua, going to psi1, psi2, psi3, and so on. So the information about this amplitude is, so this amplitude by itself is factorized. It obviously factorizes in the product of amplitude for going one step at a time from the bottom to the top. And all this amplitude for moving up, from one square to the other, takes place in a given pentagon here. Pentagon can be seen as the most elementary way of gluing two squares together. And so the amplitudes that we need to know for running out this, for carrying out this sum, are just this pentagon transition. These are, again, the amplitude for a state at the bottom psi1 to go to a state psi2 inside the pentagon. So once we understand that, we realize that we don't really need actually the full object. We can focus on this pentagonal object with arbitrary excitation at the bottom and top. And if we can find a way to construct this amplitude at any value of the tapping and for any state, we will be able to formally and in principle write any polygonal Wilson loop in the multicollinear limit as infinite sum over this pentagon. So these are the two ingredients, the only ingredients that we need to solve for the collinear limit of certain amplitude at any coupling in this field. So here is probably the part qualified as a review. This idea of Pentagon transition is not new, and by now the program for finding them is kind of over. So first of all, there are many of them because we can insert any number of excitation at the bottom and top. The Pentagon does not preserve that many symmetry of the original theory, so virtually everything that can happen will happen, including emission, absorption of excitation, as long as they do not carry some unserved quantities. So here is the most elementary process where an excitation of the bottom carrying some rapidity u or equivalently momentum pu will transit to another excitation with carrying rapidity v or momentum v. So thanks to the integrability of the theory, all the ingredients, all that we need to actually solve for all these pentagon transitions are the leading one. Okay? So once we know this elementary transition from U to V, we can immediately write down the Pentagon transition for any process involving any number of rapidity U at the bottom and any number of rapidity V at the top. So this takes a very nice factorized form, which is not proven, but is supported by many arguments and also many explicit computation that we capture. So the leftover information, as I say, are in this elementary transition. We have as many elementary transitions as we have way of pairing the elementary excitation in this theory. So we have scalar, fermion, and gluons, and all the possible pair will give us one Pentagon transition. So people have developed a bootstrap for finding this Pentagon transition, or at least guessing the answer, if you prefer. And here is a list, a comprehensive list of everything that we need to write down our solution. So they are essentially written in terms of the Flux-tube matrix that we can extract directly from the spin chain picture, up to some prefactor, which is relatively simple once written in the proper variable, which involves the Joukowski x and y, which are essentially square root of the rapidity. So this is all the information we need, and this is already concluding, in a sense, the OPE construction of the amplitude in the Collinear. There are also some rules, relatively simple rules, that allow us to generalize all of this story to non-imaginary amplitude, which correspond to Polygonal Wilson loop with extra insertion around the edge, so some insertions that can produce hard charges and so on. So at the end, what we get is a systematic expansion around the Collinear limits in the Euclidean domain. So here is a formula that we can write down in the simplest case of the hexagon. So this is something that we did last year. So this is a full finite OPE representation for the hexagonal Wilson loop. We need to sum over any number of particles on symmetry factor, because some of these particles might be identical, so there are some n factorial, integral over their momenta or equivalent rapidity, and some integrand that we can directly write in terms of this Pentagon transition using factorized ansatz for multi-particle transition. So the extra piece here, which I did not have time to explain, is a matrix part that plays an important role when the excitation of the Flux-tube can carry SU4 indices. So when they can carry our charge, our transitions are actually not numbers, complex numbers, they are matrices, tensors, and so we also need to contract all these indices together, which create quite a mess, but eventually can be collapsed into a single and simple function that we also presented in this. So this is what the final answer will look like when written in terms of this OPE decomposition. So what about the Regge limit? So here the picture is much less clear, at least to me. It's not immediately clear what are the main ingredients. So we definitely know some of the ingredients. We know that we need to know this BFKL eigenvalue. There are also extra ingredients that people have found for constructing the Regge limit of scattered amplitude with involving several gluons and so on. So, but the comprehensive and complete list of ingredients that are needed to specify and spell out the Regge kinematic, all the possible Regge kinematics of all possible amplitude is, to my knowledge, not yet known. So, of course, assuming we can identify them or understand them or organize them, the next question would be to find the expression at finite coupling. So what kind of approach can we use to construct their expression? So here there is no obvious relation to the spin chain, so there is nowhere we can go to import some information. And also the picture, the quantum mechanical picture behind this region and so on, and BFKL excitation is not as transparent, at least to me, as it is in the case of the Flux-tube. So it's much harder to develop a bootstrap and integrable bootstrap for that. Furthermore, even if we succeed in answering these 2 points, another question will remain, which is whether we can actually complete this Regge kinematics, turn it into a systematic expansion by understanding also the infinite sequence of energy surplus correction. So as you can guess, I won't be able today to answer this question. What I will show you is what we'll try to do is see how far we can go and how much we can learn or guess about all of this, starting from our OPE and our Pentagon that we have already constructed. So here is some plan of the talk. So first I will review some things that we did a few years ago already with Simon and Amit, which has to do with crossing these kinematics from the OPE to Regge at the level of the OPE, so at the level of the Flux-tube integral. So I will revisit this story with the main goal being to making it a bit simpler to manipulate for generalization to higher angle. So I will revisit it on the case of the Heptagon, which is the simplest case. Then I will discuss some application to the Heptagon and what come out of it, which is some Reggeized version or some Regge version of the Pentagon. And eventually, if time permits, I will mention some possible conjecture for higher polygons. So what is the route to the Regge kinematic? So starting from an Euclidean configuration, so for an hexagonal Wilson loop in the collinear limit, what we want to do is essentially take one of the cusps which has been flattened. So these two crosses here, you should view them as the leftover of the cusp that were here and here. So the two extra cusps that complete this square into a hexagon. These two crosses are the leftover of the cusp and so stand for some insertion of a field strength tensor at this point. So we have one free parameter which is left in the extreme tau limit, which is the sigma, which is the position or the relative position of these two excitations. So if we fix this excitation at, say, 1, then we still have the sigma we can play with. So in the Euclidean domain, which is the domain where this integral applies directly, this separation here between the top and bottom insertion is just given by the leading order by a free propagator, and it is positive. Okay? So they are space-like separated. So what we want to do is that we want to cross to the Minkowskian kinematics. So we need to turn this into something that can change sign. In particular, we need to go through the point where this expression vanishes. So it's extremely easy to identify this point. It can be plus or minus pi over 2. And this point precisely corresponds to these two insertion here becoming null separated. So this point is a point where two of the cusps of the original Wilson loop are becoming null separated. So what is happening for this integral here, when we approach this point, we can see directly at leading order at coupling, is that it is developing some singularities. If we go to sigma goes to pi over 2, here we have a logarithmic behavior, so there is a logarithmic branch point. So more generally, we expect that there will be a branch point with a certain singularity to be identified when we will hit this net-like separation. So so this is the first step towards the Regge kinematics, which is to go through this point, which is here. So we have to think about. So this is, I should have told you that before. So this is just our Poincare patch. And so we are identifying the two infinities here, the space-like infinities. So we are wrapping this object on the cylinder. And so when we are, if we are looking geometrically for this point sigma equal I pi over 2, we actually need to move this cross here outside of our Poincare patch up to a line that can intersect with this point if we follow a light ray around the cylinder. So this is the first point that we need to reach, and eventually, if we want to go all the way to Regge, what we'll have to do is to decide whether we want to go left and right at this branch point, and eventually send this sigma to infinity. So the Regge limit has to do with sending this point, this cross, all the way to a point which is antipodal to this cusp. Okay, so on a cylinder there is a point which is antipodal to any point, and this is this point that we want to reach. So BFKL computes the discontinuity through the cut, in the large sigma limit. So how do we compute this discontinuity? So first we look at what happened when we shift our sigma up to the position where there is a singularity, And what we find is that we are enhancing the integrand. So we are getting to a line, to a regime where the integrand will presumably stop converging. So there is actually an exponential pi u in the measure here, which is exactly cancelling this exponential pi u here. So if we try to move further down along the imaginary line, we will eventually make the integral diverge. So this point here, where we expect a singularity, is precisely the point where the integral is becoming marginally convergent. Now slightly up, the integral is absolutely convergent. If we are slightly above, it is just totally divergent. So how do we cross this singularity? Well, we need to do some contour manipulation. So it's extremely easy. So we first shift. And if we want to go, say, to the left part of the cut, or to the right part of the cut, we will bend the contour of integration in the up or in the down direction. In particular, it immediately follows that if we want to compute the discontinuity, we will just take the difference of these two contours of integration, and so we will end up with a contour running now along the vertical direction. So the main message is that the discontinuity through the cut in sigma is controlled by the exact same OPE integrand that we started with, this one, here, but with a contour which is now running along the imaginary direction instead of the real axis. So this contour must tend actually away from all the singularities in the rapidity plane that this integrand can have. Here I'm not going to explain you, but you should accept, you should admit that there are actually infinitely many singularities in the form of square root branch cut, and there are actually infinitely many square root branch cut which accumulate up to infinity. So what about the Regge limit? So if we want to go to Regge, we still have to take sigma goes to infinity. And what happened when we went, if we actually go, if we want to go to sigma goes to infinity, we need now to rotate this cut. So we want a discontinuity through the cut, but we want also the cut to be in a particular position such that we can go to sigma goes to plus infinity. So rotating the cut is equivalent to rotating this contour. So if it were not for the singularity here, we could very easily move the contour around or see whether we can do it or not. But because of the singularity, there are some obstacles, there is some obstruction, and we can't immediately do what we would like to. So the main idea that we had with Simon and Amit to reach this BFKL regime was to redefine the OPE integrand such that we can move the contour around. So the idea would be to modify the integrand such that this infinite sequence of cut here in the bottom or in the top half plane will disappear. So this is the freedom that we have because our contour is in this vertical position. So in particular, if we redefine our integrand by adding or subtracting exponentially small correction, we will of course not change the answer. So if we can find exponentially small correction whose effect is precisely to remove an infinite chunk of the sequence of cut, then we will be done and we will be able to cross or to move our contour around and to put it in any position we like. So this is this manipulation gives rise to something that we call the six-stop trajectory, which is closely related, hence the name sister, to the original object we started with, which is this OPE excitation. So as an elementary example, if we take the one loop energy for Flux-tube excitation, it is typically given by an expression of this type with some psi function and some argument that depend on the rapidity and on the angular momentum. And what we can do if we want to, for instance, remove all the pole of the psi function in either the upper or lower half plane is to use the reflection property of the psi function. So we take a psi function, we'll write it as a psi function with 1 minus the original argument. The difference between the two, as you probably all know, is given by some hyperbolic function, hyperbolic branch or something like that, which dramatically simplify at large u if we neglect, forget about all this exponentially small correction. What it means in practice is that for whenever we cross one of these psi, whenever we find one of these psi in our integral, we are allowed to replace whichever part we like, we dislike, sorry, by a part we like up to some I pi here. Okay. So the end result here is obviously free of singularity in either the lower or upper half plane, which is exactly what we were looking for. So it's extremely easy to actually implement this kind of manipulation at any value of the coupling for this specific problem, because energy and momentum of the excitation are known at any value of the coupling, and they have a very simple form, as they can be written as integral of cos or sine. So by separating the two exponential in the cos and by just flipping the argument of one of the two, we are exactly implementing this sister map or sister transformations that we are looking for. And so we immediately obtain any value of the coupling, a representation for the sister trajectory and the sister energies. So the final step is to put the contour in the position that we like, so either up or down. There are two sister versions of a single OPE trajectory, if you want, which depend on whether we want to move things up and things down. And this is now the starting point for going to Regge. So now we are in a good position for going to Regge. We can just ask ourselves what will happen to our object as we move sigma to plus or minus infinity. So let me skip. So what we can do is just follow the saddle point. So we can take our integral at finite coupling, looks at where is the point that gives the maximum contribution to the integral, and see what happens when we move sigma slowly but surely to infinity. And what we find is that the saddle point will essentially move up and cross the contour. So here I decided to work with this sister trajectory. I have my saddle point here, and as I move sigma to infinity, my point is moving up, 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 until it reaches the cut, and as it is reaching the cut, it must of course go below it, enter to the solution. So the conjecture, the natural conjecture will be that for the extremal case where we send sigma to plus infinity, the saddle point will eventually coincide with the BFKL saddle point. So in other words, the sister and BFKL object are two branches of the same function. Okay? The only thing that we need to do is to cross a cut, which is not something that we can easily do at recoupling because this cut is very small. But as soon as we have expressions that are valid at recoupling, we can do this kind of crossing very easily. So here is the kind of representations that we get for the eigenvalue. So everything I said, if you're familiar with Regge, is kind of equivalent to, or equivalently encoded in these two Flux-tube plots, where depending on the sign of nu square, we are in two different regimes. So BFKL on the left, the Collinear regime is on the right. What we are doing is just following the saddle point all the way from one side to the other. We can also do the same for all other ingredients. All the steps that I have explained can be implemented for other ingredients. And so this way we can obtain the BFKL version of this OPE measure, control in particular the behavior of the hexagonal Wilson. So the expression that we are getting, we can test up to very high loop order against all available data. I think it's up to 4 loop or something like that. There are also some finite coupling tests that we can do. There are some predictions made by Simon about the behavior of some BFKL eigenvalue at specific point. These are totally non-trivial inputs that we can also check with our expression. And yet another source of comparisons that we can make are at strong coupling. The problem boils down to solving some set of TBA equation. It was analyzed by this gentleman here, and we can match precisely that prediction. We can also draw some nice plotted finite coupling of these trajectories or their intercepts, so the value of the BFKL eigenvalue at the specific point, which is the origin, u equal to 0. And what we find is, so of course there is no prediction at finite coupling either than this plot, but the picture and the physics that is going on is in line with what we expect. So as a summary, there are two main steps that we should implement in order to go from OPE to BFKL. We should first do continuation in external momenta, which is to manipulate this curve such that it will go outside of the Polygonal patch and eventually go all the way to the antipodal point. And along the way, we should do an analytic continuation in the Flux-tube momentum. We should do analytic continuation in both spaces. So what about higher polygons? So this is a part which is new and in progress. So the simplest higher polygons that we can consider is an heptagon, obviously. So in this case, the excitation that is produced at the bottom will transit through a pentagon before being absorbed at the top. So instead of a single integral, what we'll get is a double integral over the two rapidity of the excitation at the bottom and top respectively. The main ingredient is this pentagon transition here, which encode again the probability for this process. If we want to convert it into an amplitude, we just need to do this Fourier transform in sigma 1 and sigma 2, which are now the two independent positions of the cusp at the bottom. So for illustration, if we look at what this P is doing on our coupling, we find that it can be expressed in terms of a simple gamma function of this. Or if you prefer position space, so we just plug this expression inside this integral, carry out the integration over u and v, and find this expression. So what are we going to do with this integral? So the simplest thing that we can do is to first look at singularities, so logarithmic singularities that were this point where cusps become null separated, and try to compute the discontinuities. We can try to compute discontinuities at specific singularities and eventually see if some enhancement happen far away along the cut of the type that could match possibly with some BFKL prediction. So here we can see three singularities, so sigma 1 and sigma 2 being plus or minus type pi over 2. So these are just two copies of the singularities that we have found before for an hexagon. And the new singularities that depend non-trivially on both sigma 1 and sigma. So the singularities here, I won't talk about it because it's much more difficult to analyze. I will focus on the easy one. So whatever polygon we consider, there are always some easy singularities which are just some copy-paste again of singularities that we had at the level of the hexagon. So these are the simplest, this is clearly the simplest starting point for investigating higher income. So what we do next is just take the double discontinuities. So we rotate, we end up with one contour, say V running like that, and another contour U running like this. And eventually do this sister trick on both rapidities. We can do this sister map independently on each rapidity. We free, by doing this, we will free the lower and upper half plane from singularities, and then we will be able to take our rapidities and move them through the cuts. So if we do that, what we get straight away is a kind of Regge version of the pentagon. So again, we just take whatever expression we have here for the pentagon, a finite coupling, and we do this system manipulation and analytic continuation, and we will get what we call a Regge pentagon. So to leading order at coupling, this Regge pentagon is nothing else than what we expect to control the Regge limit of the Heptagon amplitude, which was dubbed central emission vertex by these people, okay, and which is known, to my knowledge, only to leading numbers. So by using this formula at any value of the coupling, we can make prediction for this Regge pentagon at any loop order. So the expression, I will not write it down explicitly, but it's essentially the same structure as for a pentagon transition. It's a product of a tree or Born approximation, if you want the leading term at recoupling, times the exponential of some bilinears in psi function and derivatives. So we can do some check that these pentagons that we are getting are not totally insane. In particular, we can check that this pentagon has some decoupling pole when u is close to v, whose inverse residue is precisely the measure that we found for the hexagon before, or equivalently the impact factor of the Regge amplitude. We can also verify that this pentagon transition vanishes for some particular choice of mod number and variable nu. So for the mod 0 solution, and at nu equal plus or minus pi over 2, the excitation reduces to a single region, and the pentagon transition in this case acquires the meaning of a transition from a vacuum to an excited state, and so is fixed to a specific value that is not 0 but 1. So it must vanish. So this Pentagon transition must vanish at 0 in our normalization. So these are constraints that are essentially coming from the various collinear limits that we can engineer, and they're all done at any value of the mapping, which is probably the only consistent check that we have. So the picture which is emerging and which is in line with the kind of cartoon that people draw for understanding the physics in this BFKL regime is that a blob, which is a measure for us, or an impact factor, corresponds to the production here of a two-region state at some stage. And the central emission vertex of Pentagon transition is the amplitude for this excitation, which is produced at some point, to go to another channel. Okay? So the diagram that we will draw for this will be two blobs connected with each other with one Pentagon transition. So there is one blob for each square here, and there is a line connecting them because there is a non-trivial. There are two different cross ratios on each square here, and there is a non-trivial constellation from one square to the other. So then we can ask whether we can do bigger polygons. So last week, several papers appeared about this kind of problem, trying to understand it and what happened. So the obvious thing that we can do is to make this two-region cut propagate over a bigger distance. So that will correspond to a bigger linear diagram of this type with many more blocks because we have many more channels in the middle. So whenever we have an excitation, we have a measure again. And whenever we have two excitations which are nearby, there is a P connecting them. So what about more exotic stuff? So this is where we believe we can make a reasonable conjecture that when we are dealing with a process that involves more regions, so instead of just 2, we have 3, for instance, here, jumping to 4 on the right, that the Pentagon transition for this process, or the central emission vertex, or whatever you call it, will be just given by the product about this elementary transition. So this is a conjecture that follows from the factorization property of the OPE transition, which I've mentioned before. So here it's much more difficult to argue for why this is the right answer. So again, for me, the quantum mechanics of this region excitation is not entirely clear, so it's much harder to argue, but it's a very reasonable guess given the analogy with the OPE. So as an example, we could have a process of this type. I don't know how many edges we have here, but it's a process where we have a Regge cut of two regions that get excited into a Regge cut with three regions and eventually relax into a two Regge cut again. So the corresponding diagram will be of this type. So here in this intermediate channel we will get more block because now we have an excitation which are more freedom, more regions, so we have more rapidities to parameterize its degrees of freedom. And besides the usual lines that connect blobs which are nearby, there are also these dashed lines that introduce this denominator. This is what follows from this formula. So what kind of tests can we make? No, not that many. What we can do is some weak coupling estimates, see at which order this kind of contribution appears and whether it's reasonable. So a blob gives first one loop, a link, remove one loop. So a linear sequence which has n blob and n minus link will start at one loop as expected. And if we have a generalized sequence with the maximal number of regions which is n minus 1, then the diagram will start at n loop. So this is direct loop counting using this expression, and that seems to be rather reasonable. So one caveat about this counting is that this is all true up to this mod zero contribution again. So this mod zero as pole, the residue as a pole relate to one region. So for one region, everything will be tree-level, and so it changes a little bit the counting. So I'm out of time, so I will have to conclude. I believe that there is room for testing this conjecture, even though so far we we haven't gained so much evidence for it, but there is a thing that we can do a strong coupling following some tailoring work. There has been also many progress recently with handling this higher end on amplitude at higher loops, so maybe there is a hope to actually test this conjecture one day. And one could also imagine developing a bit further this quantum mechanical description of this region and perhaps do some direct coupling analysis of the wave function for the system and obtain this way a proof of this multi-particle transition. So here is my conclusion. So the Regge and OPE regime are the two sides of the same story. This BFKL and Collinear eigenvalues are the two branches of the same function. And what is quite remarkable is that this only becomes manifest and tractable at finite time. So crossing the kinematics in real space become equivalent to crossing a cut in rapidity space. So there are many open questions. So among the questions is whether what we are saying is correct. So for instance, the completeness of state, is it true that we can parameterize all the n region state in terms of factorized two region state? Can new state appear for n equal a, for instance? Can we go all the way from the Collinear to Regge for higher n-gon, and this way maybe prove or disprove this conjecture? Or is there some islands that we will never reach starting from the OPE? So here are the many questions that we might be able to answer in the future.
So, is there any question for Benjamin?
Just to be clear, all these multi-region contributions, they appear at sort of leading power law, because in principle you could look for things that are power suppressed too.
So it's not energy suppressed. It's appear at the same level as the leading region contribution.
Are you also thinking about subleading power suppressed corrections, or is that a whole different story?
Okay, so subleading power suppressed is a much more exotic subject, and I have nothing to say about it.
All right, if there's no more questions, let's thank Benjamin again.